So let's talk a little bit about integers and how did integers come about. So this section is about addition, subtraction, and integers. Addition and subtraction. The simplest mathematical operation we know is addition. The inverse of addition is subtraction. Two operations are inverses if one undoes the other. So inverse operations, they're a very important component and they apply to all of mathematics, okay? So again, when you think of inverse, think of one undoes the other. So each time a marble is dropped in a jar, we are doing addition. Each time a marble is removed from a jar, we are doing subtraction. And the number line allows us to think of addition in a new way. And let's see an example of that. Let's find the sum of 4 and 5 on a number line. The number plus 4 is 4 steps to the right. So we would go 1, 2, 3, 4. 4 steps to the right. And start at 0. It takes you to 4. And then if we want to add 5, we move 5 steps to the right. 1, 2, 3, 4, and we land at 5, starting at 0. To find the sum 4 plus 5, we start at 0, take 4 steps to the right for the first number, then start where you ended after those first steps. Take 5 more steps to the right to represent adding 5. If we were walking, we could look down and see we are standing at the number 9. So we started with our 4, took 4 steps to the right. We added our 5, we took 4 steps to the right, and now we are at 9. Again, this is for whole numbers. The commutative property of addition is another property we often use. And it doesn't matter what the order is. So in this case, addition would be commutative. 4 plus 5 equals 5, and 5 plus 4 equals the same thing. Let's test that out. We found that 4 plus 5 equals 9. How about 5 plus 4? Let's check it out. Going to do the same thing. We're going to go 5 steps to the right to step at 5, and we're going to add 4 more steps to the right, and we still get at 9. This is the commutative property of addition. You can take any number, and as long as there's a plus sign, you can move them to either side. Addition is commutative in this case. Again, 4 plus 5 gave us 9, and 5 plus 4 also gave us 9. But there's nothing special about these numbers. This is true for any number, okay? So any number you say 7 plus 9, 9 plus 7, it doesn't matter. They still have the same commutative property of addition. Inverse operations. Remember, operations are inverses when one of them undoes what the other does. So what would undo adding 5? What would undo adding 5 is if we subtract 5. So addition and subtraction are inverses. So for example, adding a number and then subtracting that same number leaves you where you started. So starting at 4, add 5, and then subtract 5 still allows us to end up right at 4. This is what we mean when we say inverse. They undo each other. This is true for any two whole numbers. You start with A, add B, then subtract B. You will end up with the number you began with, A. So that's all those variables mean down there, is that you can plug in any number for A, any number for B, and you're still going to end up back at A because these two will undo each other. We started with the addition question. What number results when we add 5 and 4? The answer is 9. That leads to two new related subtraction questions. Starting with 9, what number do we get when we subtract 5? we get 4. Starting with 9, what number do we get when we subtract 4? We get 5. Subtraction was invented to undo addition, but it now can be used to ask some new questions. Here's what 9 minus 5 looks like on the number line. 9 minus 5 brings us back to 4. Here's what 9 minus 4 looks like on the number line. 9 minus 4, 1, 2, 3, 4 brings us back to 5. We need more numbers. Subtraction was invented to undo addition, but this new operation allows us to ask new questions. And the number system up to that point couldn't provide answers because they only had whole numbers. So for example, what is the result of subtracting 7 from 4? We're left with a mystery. Something needs to go here, but we don't have any whole numbers after 0. So there was no answer to the questions like this in the whole number system, which was all there was until about 500 years ago. Then we invented negative numbers. This led to this invention. They were called negative from the Latin negare, which means to deny, since people denied that such numbers could exist. They weren't used much until the Renaissance, and we were only fully accepted in the 1800s. If you have trouble with negative numbers, so did most everyone else, so don't feel any kind of way. But this number would be a -3 looking at this number line. Let's check it out some more. Adding the negative numbers to the whole numbers yields the integers. Okay? Adding negative numbers to the whole numbers yields integers. In this case, ... at the left and right means that the sequence continues in both directions forever, meaning these numbers will get larger and larger and not larger, or smaller and smaller but negative. There is no largest integer, nor is there a smallest integer. But the key part is they are all whole numbers that now have negative connotations. So below we see this shows only integers. And remember, this arrow will continue 11, 12, 13, 100, 100,000, 10,000, millions, as long as it's positive numbers. And this arrow on the negative side will continue -1,000, -100, -500, -1,000,000, all the way down. It's just going to keep going forever and ever. We just don't have a paper that is large enough to hold all those numbers. Integers on the number line. So we have 0. It's neither positive or negative. Then we have positive integers from 0 to 5, and our negative integers will go below the 0. This concludes this portion of the video. Get ready to take a couple questions to see if you can identify integers.